Actually, by even just looking what's in this sample plot, the mid-column, firstly is like a confidence building exercise. Like, you know all of these things. So there are like a ton of questions here. But I don't know. You know, inverse trigonometry too. Well, one, use inverse trigonometry to find some angles given some information in a triangle. A right triangle if you're going to use inverse trig and right triangle trigonometry. You know how to figure out what quadrants various inverse trig functions sit. You can compute these compositions. We've done a few examples of that. Once you have inverse trigonometry, that's the whole point of inverse trig, you can use it to solve trig equations. That's the motivation for why it's worth studying. Solve some trig equations. And there's like a lot of those. But things you know how to do. Before the break started, we developed these things called law of sines and law of cosines, which let you solve non-right triangle problems. Go through the process of doing it. This whole set culminates with, well, one, go through and just completely solve these triangle problems. Some of them have multiple solutions, but you know how to do multiple solutions. Right? Like whenever you use law of sines to find an angle, you need to ask yourself, might that angle be obtuse? If it is, then you just need to find the obtuse option along with the acute option. And if you can put together a bunch of triangles, then you can solve more complicated things. There's some complicated looking diagram. By finding various bits in that diagram one at a time, you can find out anything you want in terms of it. What remains in here is the stuff we haven't covered yet. Well, mostly. Yeah. Oh no, there needs to be something added here, because I am going to ask you to prove a trig identity on the midterm. So that probably should be added to this document. I will definitely ask you to prove a trig identity on the midterm. There are angle addition formulas. These angle addition formulas say how to realize a trig function at a sum of angles in terms of trig functions at the sum ends. And we don't have those formulas yet. We'll have them by the end of today. In fact, we'll have them within the next 5 minutes. Once you have them, you'll be able to complete problems up through 33 in here. It's probably not so big a stretch to say, well, if you know how to add two angles together, then you can figure out how to compute cosine of 2 times an angle. Or sine of 2 times an angle. If you know how to double an angle, it's probably not a stretch to say, well, I can figure out how to divide an angle by 2. Those are the last little bits of content we'll get before the midterm. They'll show up on the midterm. Cool. So, with that in mind, let's start in on talking about the angle addition formulas. I will also ask you to prove trig identities. Cool. So, let's talk about angle addition. So the angle addition formulas say the following. If I give you two numbers a and b, then you can compute cosine of a plus b in terms of cosine of a and cosine of b. And I'm going to write down something that is not true. Cosine of a plus b is not the same as cosine of a plus cosine of b. You can't just add together the cosines and hope that that's going to give you the sum of the cosine of the sum. That's never correct. Instead, the cosine of a plus b is given by the following formula. Cosine of a, cosine of b. I'm going to emphasize that this is a minus sign by drawing it in blue. Minus sine of a, sine of b. And during the course of today, I'm not going to try to prove that formula. Not that it's hard, it's just there's more directed things I want to do with the time. If you want a proof of it, the proof isn't terribly hard. There are two proofs that appear as extra credit. One of which just comes from studying those two diagrams. I take a triangle with this angle being a minus b, and rotate it by an extra angle of b. Study that diagram, angle subtraction will be handed to you. You can also study this triangle diagram, and eventually it'll hand you trig functions at a plus b. Extra credit to you. So there's a formula for the cosine of a plus b. I'm not going to try to prove it, but what's something we could do that would at least be convincing that a formula like that should be true? Could we try to graph it? Yeah. There are two variables, so maybe I'll set one of the variables to be constant, the other one I'll allow to vary. This Desmos link will go to the graph of cosine of a plus b, along with this thing in pink. There it is. So there it is for a equal to minus 2. There's the cosine of negative 2 plus x. There's the formula cosine a cosine x minus sine a sine x. Do those two things look like they're pretty close to exact? And in fact, we can start varying a. Do they seem to be being more or less exact? Yeah. And I'm going to make that go away because it is just hypnotic if you let it keep going. Cool. So there's what happens when you add two angles together and compute their cosine. What do you think will happen if I subtract? How do you think the formula will change? Well, what is subtraction? Opposite of addition. But it also is addition. You can do subtraction by adding a negative sign in front of one of them. So what I'm about to do is try to convince you that you don't necessarily need to have this formula memorized, because you can say, well, cosine of a minus b is the cosine of a plus negative b. Is that true? Can I now use the formula that's to the left from that? Yeah. I'll get cosine a cosine negative b. Does cosine care about a negative inside of the parentheses? No, cosine's even. So I'll get cosine a cosine b. There should be a negative in front of the b, but cosine doesn't care about that negative anyway. Minus sine a sine. And I'm going to take advantage of erasable pens in a moment. So if you can't erase, maybe hold off on copying down. What can I do with the negative inside of the sign? I could pull it out of the sign, and then it would cancel with the negative that I already have out front. Cool. Let's cancel those negatives. So cosine of a minus b is the same as cosine a cosine b plus sine a sine b. Neato. And we can do something similar for sine, and I'll do the same sort of thing. I'll write down the formula. I won't try to convince you that it's true. I'll leave that as an extra credit. Sine of a plus b is equal to sine a cosine b plus cosine a sine b. If you want to subtract, then that plus just becomes a minus. Sine a cosine b minus cosine a sine b. Cool. That seems pretty good. So we have these formulas. Let's do some stuff with them. So here's the most obvious application. If I give you an angle, and you can realize that angle as a sum or difference of angles that you understand, well, then you can compute trig functions using these formulas. So let's try that with, here's an example, 5 pi over 12. So, can we realize 5 pi over 12 as a sum or difference of some angles whose trig functions we understand? And we don't know that many trig functions, so there aren't that many options here. In fact, let's try to guess one. give me two angles that appear on your unit circle, which you think might have some chance of adding up to 5 pi over 12. If they don't, then we'll just like tweak it. So give me an angle that's on your unit circle. So, the unit circle gives you trig functions at the following. I guess this isn't my filled-in copy, and it's the one that like pointed funny, but whatever. They're the angles that we know how to compute trig tangents at. Just let's try two of them, see if they add up to 5 pi over 12. If they do, then we win. If they don't, then we need to try again. So just give me two candidates that are worth adding together to try to get 5 pi over 12.
Pi over 4 and pi over 6.
Let's try pi over 4 and pi over 6. If it works, great. If it doesn't, that's fine too. I think those ones do work. I think you have... So let's just try it. Pi over 4. Let's try pi over 4 plus pi over 6. So I guess we need to get a common denominator to write those fractions. What's the common denominator between the 4 and the 6? Just say louder. 2. Oh, well, you get a common denominator, like you need a common multiple of 4 and 6, and then you like multiply and divide by a thing. So 12. 12 is 4 times 3, so that's 3 pi over 12 is the 4 pi, plus 2 pi over 12. Oh, neato, is that 5 pi over 12? Awesome, let's use that. So 5 pi over 12 is equal to pi over 4 plus pi over 6, pi over 6. So that means I can compute trig functions at 5 pi over 12 using that fact. And I think I'll do cosine, and then I'll leave it to you to do sine. So, maybe I'll even add some helpful color coding. Pink. This will be green. I've got a better green. So, cosine of pi over 12 is a sum. So this will be cosine of A cosine of B. So cosine of pi over 4 times cosine of pi over 6. This is a plus, so I now need to subtract sine pi over 4 times sine pi over 6. Cool. So far, so good? Are all of these individual trig values numbers that I know? Oh, God damn it. I said I would color code them, I just didn't. Sine pi over 6. So cosine A, cosine B minus sine A, sine B. What's the cosine of pi over 4? Like your root 2 over 2? Cosine pi over 6? Minus is still minus. Sine of pi over 4? Sine of pi over 6. Nice. So in some sense, there's a final answer. Is that a final answer that simplifies? Yeah, it looks like the fractions already have a common denominator. You multiply out the sum ends, you'll get that common denominator being 4. And now you just subtract the numerators. Equals over 4 2 times 3 is 6, so root 6 minus root 2. Gesundheit. That seems pretty okay. Cool. Think you could do the same thing for the sine of 5 pi over 12? Do it. Oh, yeah, absolutely. Yeah, sorry, I asked if people needed extra copies, but like, you walked in like a minute after that. Thank you. This is from 2, right? Awesome. Once you have an answer, if you compared it with someone around you, attendance is really low today. Is it like a special day somehow? Yeah, but like, there are tons of Fridays, and most of them haven't been this low.
I just woke up at 8:30.
I mean, you made it though. Oh, no, as long as like you didn't actually get a ticket or cause any accidents, right? No harm, no foul. Cool. What y'all getting? It's something divided by 4. There's probably the square root of 6 and the square root of 2 in it. But what don't really go in?
Is it root 6 plus root 2?
Is it? People agree? I hear a root 6 plus root 2. Do I hear a call for me to go through the computation? All right, let's do it. So, I hear that as a suggested resolution. Let's talk through the process. So what was the first step on your way to getting that?
I just wrote down all the individual pieces of the sine A and cosine B.
Cool. So you wrote that down. I guess there's your choice of A. There's your choice of B. So this will be sine of A, cosine of B. That 4 is not sufficiently legible. That's a little better. Plus cosine of A, sine of B. So far, so good? All right. Are those all angles that you see on your unicycle, so you just know it there? Yeah. What's the sine of pi over 4?
2 over 2.
Root 2 over 2. Cosine pi over 6.
Root 3 over 2.
Root 3 over 2. Plus cosine pi over 4.
Root 2 over 2.
Root 2 over 2. Sine of pi over 6. Does that work out to the thing that's pulled out to the right? Cool, yeah. And I don't know, just in order to reinforce that you can do things to double check your answers when you're feeling non-confident, Could we also just ask the calculator to directly compute this and that and see if they agree? Yeah. And I'll even use the least powerful option I have available. I'll use the Google calculator. Let's compute. Should I check cosine or sine? Cosine? Sine. All right. Sine of 5 times pi divided by 12. And Google will default to thinking in radians, but it even says so right there. 0.97-ish. Square root of 6 plus square root of 2 divided by 4. Is that the same number as it was before? Mm-hmm. Awesome. I think that they actually agree. So there's one thing you can do with angle addition formulas. It turns out that using the same idea, you can now exactly compute all the trig functions at any multiple of pi over 12 using information you already have. Here's 5 pi over 12. You could do something similar to get pi over 12. 2 pi over 12 is pi over 6, which you already know. 3 pi over 12 is pi over 4, which you already know, and so on. So this lets you do new computations that you couldn't before. Let's use it to check something else that you already know. We have a trig identity that says something about what sine of pi over 2 minus x is equal to. And you just remember what it is? Let's remember what it is by doing some graphing. Let's graph sine of pi over 2 minus x. Does that curve look like a curve that you recognize? What's it look like? Cosine. Let's just double check that by. Cool. That check out? Mm-hmm. All right. So it sure seems like sine of pi over 2 minus x is equal to cosine x. Let's see if angle addition agrees with this. Because this says that sine of an angle minus an angle is equal to cosine of x. That looks like something we could just use angle subtraction to also check. Yeah, let's do it. So I guess I'll use pi over 2 as A, x as B, and I'll use the angle subtraction formula for sine. So I'll see sine of pi over 2 cosine of x, sine A, cosine B. I have a minus sign there, so it'll be minus. Oh, yeah. Let's just do this. So sine A, cosine B. Sine A, cosine B minus cosine A, sine B. Minus cosine pi over 2 sine x. All right, so let's see what that becomes. I see those pi over 2s, those are angles you know on your unit circle. There are also maybe ones you don't even need to look at that you're on unit circle to know. What's the sine of pi over 2? 1. If I start at 0 and rotate up by a right angle, I'll get to a y value of 1. This is 1. What about the cosine of pi over 2? Here is 0. Right, the x value when you rotate by pi over 2 is 0. Oh, neat. Is that just cosine of x then? All right, cool. So, here's one payoff. Do you remember when we got all of these symmetry identities for trig functions? They all looked something like this. Are each of those just two angles added together though? So ostensibly, you could now reconstruct all of these just out of angle addition. I mean, it's somehow more complicated. You're using a big hammer to do something that's actually really quite easy to do. Cool. So here's another thing you can do. So let's suppose that instead of an example like this, where I explicitly give you an angle that's a sum of two angles whose trig functions you have numeric values for because of the unit circle, what if I just tell you, here's an angle whose cosine you know, here's another angle whose cosine you know. Let's try to compute cosine of their sum. That look like something we might be able to do? Yeah. And in order to get a strategy, I'm going to hit these bullet points in a somewhat silly order. And then I'm going to start with the third bullet point, I'll walk it a little bit, and then we'll find out that we need the things in the first two bullet points. So, do we have a formula for cosine of a plus b in terms of a and b individually? Yeah, it's at the top of your page. I guess it's off the top of the screen right now. It is, well, read it off. What's the cosine of a plus b? Cosine A, cosine B. So the product of the cosines minus the product of the sines. All right. So that means in order to use this tool, I need to know cosine A, cosine B, sine A, and sine B. Do I know cosine A? What is cosine A? Say louder. 3 over 5. Do we know cosine B? 5 over 14. Do we know sine A? No. But could we? Yeah, right. If you know cosine, then you can figure out what sine is. And let's try to do exactly that. Let's try to compute sine of A and sine of B using the information that's given in this problem. So let's compute sine of A. So let's do this in pink. I'm going to do this in pink. There's sine A. I'll underline in pink the information that is relevant. So cosine A is 3/5 and A is between 0 and pi over 2. Is that enough information to figure out sine of A? In fact, well, how many people here just already know how to find sine of A given that? Oh, I expect you all have seen it. So let's walk through this one of two different ways. Either using a right triangle or using sine squared plus cosine squared is 1. Right triangle? Sine squared plus cosine is 1. Let's use that one then. So let's try to find sine A using this fact. So I know that sine squared of A plus cosine squared of A is equal to 1. Do we know what cosine of A is? Yeah, in this problem it's 3/5, I think. So that means I'm going to play the game where I'm going to replace sine of A by S, just so I don't have to write sine of A all the time. So I'll get S squared, the thing that I would like, plus 3/5 squared equals 1. That now look like something we could solve for S. In fact, how many people just oh, I don't know what that S is going to be. Should I finish the algebra? Okay, then I'll wait for someone else to finish the algebra. What are we getting? 4 over 5. Do I hear a second? And now that you hear that 4 over 5, does this maybe remind you of some phrase like a 3, 4, 5 right triangle? Yeah, so I mean, I think that you could have guessed this beforehand. All right, 4 over 5. Oh, maybe I'll emphasize one last point. So depending on how careful you roll with undoing a square root with the square root, you would have got like a plus or minus 4/5. Why plus?
Oh, because of the range.
In that range is sign positive or negative? Nice. Okay, so now we know sine of A is 4/5. Let's put that here. And let's make it clear that this is an addition sign. No, I want to do a subtraction there. Well, this is why my pens have erasers. Sine of A, sine of B. Is that something we could similarly compute? And maybe just for emphasis, like there are the two different ways to approach this. There's this very algebraic way. There's also the draw triangle way. I think I'll also draw a triangle. So let's try to determine sine of B. This one I will do in blue. Let's try to compute sine of B. I know cosine of B is 5/14, and B is in between 3 pi over 2 and 2 pi. So instead of doing this purely algebraic strategy, let's draw a triangle. And let's start with this information. What quadrant is B in? Quadrant 1? Do we agree? All right. So we have this. Let's draw a picture. There it is. It's an angle in quadrant 4. Let's draw a right triangle that we will use to study. I know that cosine of B is 5/14. So I can label some sides of that triangle, right? SOHCAHTOA, cosine is adjacent over hypotenuse. 5/14. I'll label that side as opposite. Could I use this to figure out the opposite side? Yeah, right? I will see opposite squared plus 5 squared equals 14 squared. Cool. In looking at that, does anyone just like recognize what the opposite side length is going to be? I hear 12. And right, the 12 squared plus 5 squared is 14 squared. That's an example of what's called a Pythagorean triple. If you didn't recognize that, you could like solve and find it. In fact, should I go through the solving to find it? Okay, cool. So the opposite side length is 12, and I'm going to write down something slightly wrong. So sine of B is opposite over hypotenuse, 14. Why did what's bad about what I just did?
It's not negative.
It's not negative. The right answer is negative because it's in quadrant. I forgot the quadrant information. That's just something you always need to remember when you use these this triangle argument. You need to remember quadrant information. You always need to remember quadrant information. All right, let's put that down. Times negative 12 over 13. Is that now everything I needed to do angle addition? Now it's just a matter of finishing it up. This is equal to, gosh, 3 times 5. You might want to cancel those 5s, but I think I don't want to because, like, this has a 5, but it won't cancel with anything there, so I need that common denominator of 5 times 13 anyway. 5 times 13, I believe, is 65. So the denominator is 65. 3 times 5 is 15. Double negative becomes positive. 4 times 12 is 48. All right. And like the numbers are getting big, but not huge. It's like if you need to bust out a calculator, do it. But I think that's 63 over 65. Awesome. Do we have everything we need to compute the sine of a plus b? In fact, how many people have done already because I was being slow? Okay, I guess I wasn't being too slow. Do it then. And maybe as you do that, I will say that as a bit of motivation, I like to throw this kind of problem on things like exams. Cool, so I'm obviously not doing it myself. So, once you have an answer, and maybe you compared it with people around you,
I get negative 16 over 65.
do I hear a second? Nice. So, if I tell you enough information to pin down two angles, which I did in this one, I told you the cosines in the quadrant. That's enough to figure out what the angle is. That's enough to figure out cosine A plus B sine of A plus B. And maybe I'll make one little observation. So that means that, well, I certainly haven't used the word Pythagorean triple in this class before. But people have heard that term Pythagorean triple at some point in the past. Yeah, it's just three whole numbers which satisfy a squared plus b squared equals c squared. So like 3, 4, 5 is a Pythagorean triple, 5, 12, 14 is a Pythagorean triple. This gives you a new Pythagorean triple. 63, 16, and 65 is a Pythagorean triple. And why should that be the case? Well, this 63 over 65 tells you that with this angle A plus B, you can draw a right triangle with adjacent side 63, hypotenuse 65, and opposite side length 16. And now those are explicitly sides on a right triangle. There's a new Pythagorean triple. So whenever you see two different Pythagorean triples, you can do angle addition to get a new Pythagorean triple. That's not important to this class, but it's like a slick little observation to see. This is one way of cooking up infinitely many Pythagorean triples now. You could like keep doing this angle addition stuff. Awesome. So, I'm looking at the clock. I'm seeing I have 9 minutes. I've covered one of the 2 pages I wanted to cover today. So I'm going to go slightly out of order. Tomorrow will be all about double angle stuff. So I won't start with the segue to double angles. I think I'm going to think about angle addition for tangent. And I'm even going to cheat a little bit. I'm going to skip where it comes from and jump down to the bottom of the page where the formula for angle addition for tangent appears. So here are some formulas. I think I'm going to approach this page roughly starting at the bottom and going up, which is counterintuitive. The angle addition formula for tangent says the tangent of A plus B is equal to the tangent of A plus the tangent of B all over 1 minus tangent A tangent B. And if you subtract instead, you will subtract the tangents in the numerator. And then the subtraction in the denominator becomes a plus. And so here's the same point as before. If I give you two angles and I give you enough information to compute tangent of those two angles, then you can compute the tangent of the sum. And I think one example, well, let's do this example. Let's try to use this to compute tangent of 7 pi over 12. And the idea here is the same as 5 pi over 12. So look at your unit circle. Do you see two candidate angles which seem likely to add up to 7 pi over 12? And let's just like try two angles. I don't know. I'm going to do like some that are wrong. Let's try pi over 3, I don't know, minus pi over 4, and just see what happens. What's the common denominator between those two? 12. That's good. This will become 4 pi over 12 minus 3 pi over 12. Does that work out to 7 pi over 12? Well, balls. That means that this just wasn't the right pair of things to subtract together to get 5 pi over 12. But does this give anyone an idea of how to change it? I think if that minus were a plus, I'd be happy. Oh, cool. So this is what I meant on like the 5 pi over 12, and I said, well, let's just try something. If it doesn't work, then it'll tell us how to change it. And I didn't get to demo that because you just like told me the right thing to try off the bat, so I didn't get to do the supervision. So let's use that. Tangent of 7 pi over 12 is equal to the tangent of pi over 3 plus pi over 4 equals, now I can use this formula. Tangent of pi over 3 plus tangent of pi over 4 all over 1 minus tangent of pi over 3 multiplied by tangent of pi over 4. Are those all numbers that we know? Yeah, depending on how well you've internalized unit circle values. What's the tangent of pi over 3? Well, see, that's like the steepest angle you know on the unit circle. And it's pi over 6, pi over 4, pi over 3. And then pi over 2 is bottom. Pi over 3 corresponds to a tangent of root 3, I think. Because that one's root 3 over 3. This one's root 3. Root 3 plus pi over 4 has cosine equal to sine. So what's the tangent of pi over 4? Just 1. It's going to be root 2 over 2 over root 2 over 2 divided by 1 minus root 3 times 1. So I think this is simplified enough. 1 plus root 3 divided by 1 minus root 3. There's the tangent of 7 pi over 12. That computation feel pretty good, okay? All right, so I have, I think, enough time to explain where angle addition for tangent comes from. So here's a strategy. I know what angle addition says for sine and cosine. Can I write tangent in terms of sine and cosine? Let's start there. Tangent is sine over cosine. So this is equal to the sine of a plus b divided by the cosine of a plus b. Does that seem okay? Do I know the sine of a plus b? Yeah, I mean, you might need to flip to the previous page to like remember what it is because, well, I don't know, how many people had already seen these angle addition formulas at some point in their past? Okay, that's roughly the proportion that I would have expected since like, we're close to the end of the semester. I hope I've come up with something new. Sine of a plus b is sine a cosine b plus the same thing but with the sine and cosine switched. Sine a cosine b plus cosine a sine b. Then in the denominator, cosine cosine minus sine sine. Cosine a cosine b minus sine a sine b. All right. Cool. So ostensibly, like, there is a version of angle addition for tangent. But it's like not a very satisfying angle addition formula for tangent because it says to compute tangent, you need to compute sine and cosine. It's more beautiful to know the formula that just needs tangent. So if I want to get tangents to show up, let's see, I see a sine of a. If that sine of a were divided by cosine of a, that would make me happy. But I can't just divide one thing by cosine of a. I have to divide the numerator and denominator by cosine of a. Right, as long as you are doing something multiplication and you do it to the whole numerator and the whole denominator, you don't change the fraction. I also see a sine of b. If I divided by cosine of b, that would become a tangent. So let's do that. Let's also divide by cosine b, and then we'll just see what happens. Anyway, there's nothing fancy that I just did. This is just, I guess, the process you would use to prove this trig identity. Tangent of a plus b is then sine of a cosine b divided by cosine a cosine b plus cosine a sine b divided by cosine a cosine b all over cosine a cosine b divided by cosine a cosine b minus sine a sine b all over cosine a cosine b. So I think that's what is known, what I would refer to as a step that is easier done than said. All I did is I distributed that division, but actually writing all of those lines was a pain. So easier done than said. It was an easy step but hard to write down. Now that you see that, does anything cancel? Is there a cosine divided by cosine that I can throw away? I hope so. Those two can cancel. Oh, that leaves me with sine over cosine. What's sine over cosine? Tangent. That's where that tangent A comes from. Cosine A, cosine B. Those cancel, leaving me with tangent B. Everything in this term cancels, leaving me with 1. There's tangent A, there's tangent B. That's where the angle addition formula for tangent is. And so there's no deep factor. It's just the same idea. If you know something for sine and you know something for cosine, you can picture it. You know. And I am only slightly over time, but that means I can probably stop. thing that I will request you do in advance of when we meet on Monday is this. Figure out the double angle formula by using angle addition. Yeah, I guess you can have it.
Remember early?
Yeah, you're like 8 minutes on it.